Hi guys, in this video we will look at the Benzyne mechanism. Let's begin by reviewing a little bit from the last video and the first page here of the substitution of leaving groups on aromatic rings handout. Reaction A we saw was a traditional example of a NAS mechanism. We have a traditional leaving group that has a strong electron withdrawing group, ortho or para, ortho in this case, and so it is a good substrate for a NAS mechanism, and the nucleophile here can displace the leaving group. But in reaction B, we saw there was no reaction, and as we now know, the chlorine does not have a strong electron withdrawing group, ortho or para. The methoxy group, which is ortho, is a strong donating group. And that comes from considering that as a group 1 in the EAS discussion. But if you try this reaction B at higher temperature, and I'm talking significantly higher, 300 degrees in this case, we can get a reaction. And we can replace the chlorine with the nucleophile. But interestingly, we also get another product here. And somehow the nucleophile ends up on the adjacent carbon to where the leaving group was originally. Thus, isomers are going to be formed. Now, this is not an NAS mechanism because we know that the NAS mechanism only occurs when we have that strong electron withdrawing group, ortho or para, to the leaving group. Okay, so it's clearly not NAS. Also, we would not expect the nucleophile to end up on the next door carbon, the adjacent carbon, if we did an NAS mechanism. So, what is the mechanism? Well, it turns out it is what we call a Benzyne mechanism. The Benzyne mechanism is not easy to do. It requires fairly harsh conditions, high heat, sometimes even pressure. That implies that some type of intermediate is pretty high in energy. Let's look at the Benzyne mechanism. If we turn over here, now we've already stated these three things here. Here's an example reaction. If you take chlorobenzene and try to react it with KOH to maybe displace the chlorine with a hydroxy group in this case, the hydroxide nucleophile, if you do this at room temperature, no reaction. And this is analogous to what we said over here using the ethoxide. Okay, 25 degrees Celsius, no reaction. But if you treat chlorobenzene with potassium hydroxide at 300 degrees Celsius and under 2500 psi of pressure, we can get a reaction. Now, it does require an acidic workup, and we will explain why. And we can replace the chlorine with a OH group here. And the chlorine is released, or it leaves as chloride. So let's show a mechanism for this. Now, hydroxide could possibly attack this carbon. First off, we would never attack it and kick off the chlorine. That would be SN2. We certainly don't do SN2 on an sp2 halide. We've talked about that. We could also attack the carbon and break the pi bond away, but that would be the first step of an NAS. And we've already said several times that the NAS mechanism is not going to occur here. So what else could we do in the first step? Well, it turns out that the first step involves the nucleophile acting as a base and taking the adjacent H. These electrons bond to H, these electrons stay behind, and we would get that anion, a carbanion, plus water here in this case. Now, this is a plain carbanion. There is no resonance here. It is not resonance stabilized. The only thing it has going for it is sp2 hybridized. Now that is a traditional acid-base reaction. Now the equilibrium probably, or no doubt, favors the starting side. All right? The pKa here is probably about 30. pK of water is 16. Let's say about 30, about 16. We see the weaker acid is favored by 10 to the 14. That's huge. But that doesn't mean we can't form some of this. Now at this point, the mechanism is known to proceed by these electrons moving in here and kicking off the chlorine. We can go back to anytime you can make a pi bond with a lone pair and kick off a leaving group, that tends to be easy to do. Now, it's not as easy here for a couple of reasons, but it falls under that sort of umbrella statement. And if we do that, we end up with a triple bond between the two carbons in the benzene ring, plus Cl minus. And there's the Cl minus we are going to form. But this species here is called a benzyne, like an alkyne, carbon-carbon triple bond. All right? And that's why the mechanism is called a benzyne mechanism. Now, this is a very strained alkyne. Alkynes are typically, all right, I'll just draw a simple acetylene, all right. This carbon is sp linear. And so the bond angle between the CCH is 180 degrees, linear. All right? But look at this bond angle. This is 120. Very strained for an hybridized carbon. Both of the carbons are strained. Bond strain. All right, we can call this very unstable, even though it's net neutral. Now, is it really a triple bond? If we look here, it sort of talks about it. All right, I called it sp hybridized. It's actually known to be sp2 hybridized. And the second pi bond is really coming from overlap of hybrid orbitals. Because of the geometry constraints, these two carbons can actually not become sp. All right? When I said they were sp, they look like they should be, but they're actually not. They actually remain sp2. And one of the pi bonds is from p orbital overlap. The other pi bond is from side-to-side overlap of hybrids. Now, usually our hybrids have head-to-head overlap, a sigma bond. So this is a very strange case of hybrids making a pi bond. There's a good amount of theory to this. Okay, some chemists argue about this. Is it really a pi bond? Whatnot. There could be some different discussion here. Basically, let's move from here. At this point, it's actually electrophilic. All right, and why? And in this case, the nucleophile that reacts with the electrophile is water, and these electrons come in here and add to the carbon and push these electrons back. And that will give all right, double bond now. The other pi bond gets pushed back onto carbon as a lone pair, and that's a minus. And now we have an oxygen with H and H, and that's a plus. And so this was nucleophilic addition. By the way, back over here we did an elimination of the leaving group. Now at this point we will do H plus transfer, because this looks like a base, it needs a proton, and then this looks like it needs a base to take a proton to go neutral. And we've talked about proton transfers before. They're probably intermolecular. We don't need to show a mechanism. We do need to understand what's going on, and that's going to give that. All right. Now there is an H there. There's no H there, there's no H there, there's no H there, because that H was removed by the base over here. But now there's an H there. It's a standard carbon with an undrawn H, and there's your product. But, hold on. Let me draw this bond out here. Because we're under basic conditions. We just made a acidic product under basic conditions. Now it has a pKa of about 10, phenol. The base will then deprotonate this to give the phenoxide plus water. And this is 16. Which side's favored, 10 or 16? Well, 16 is favored. The weaker acid, we see that the phenoxide is favored. All right. And this is actually in step 1. Step 1 being reaction with KOH at very high temperature and very high pressure. Why do we need acidic workup? Because we need to put the proton on. All right. This is going to be some acid here. That's generic. Maybe we add HCl. And these electrons take the H, leave that behind. And so we would then get our phenol. Any other acid here, HBr, sulfuric acid, something to drive the equilibrium to the phenol. All right. This is a case where we made a acidic product under basic conditions. The product will thus exist in the basic form. We then have to put the proton on. A long time ago, I came up with an analogy that's so stupid it's hard to forget. Maybe a student helped me come up with it, but if you knit a sweater in the swimming pool, it will be wet when you're done. You will then have to dry it. If you make an acidic product under basic conditions, it will exist in the basic form. You will then have to put the proton back on in a separate step. You cannot keep hydroxide from doing this acid-base chemistry. You cannot say, okay, hydroxide, only react with chlorobenzene. As soon as you start making some phenol, the hydroxide will come over here. So you actually need two equivalents of KOH. One to do the reaction and one to deprotonate the product. You then need to come in with a strong acid to put the proton back on. Okay. Why does this reaction take so much heat or pressure? It's because one of these steps over here is very difficult. Now, this varies. Sometimes folks will not show this intermediate. They'll go directly to the alkyne by doing like an E2 elimination. I would prefer you do it like this. There is evidence that the anion is formed first and then it eliminates. Rate determining step actually can vary. In some cases, this may be the rate determining step. In other cases, this may be the rate determining step. And there's actually a question in the workbook that gets at this. Depending on the halogen, ultimately, there's lots of fine details that can be discussed here. Okay. One other very important aspect of this mechanism. Why did the nucleophile attack this top carbon of the benzyne? I only did it because that's where the leaving group was. But why not attack here and move the pi electrons this way? The benzyne is symmetrical. With benzynes, you can always attack either carbon. All right? And that's how we're going to get isomers. Now, we don't actually get isomers in this example because no matter which carbon you attack, you're going to get phenol. But back over in the reaction shown on the warm-up page, we form the benzyne here. And by the way, it may be easier to form the benzyne if the pi bond is drawn here, here, and here. And we can envision the benzyne being formed like this. And once you form the benzyne, the nucleophile can attack either carbon. Now in this case, because there's an existing substituent, you will get two different products. If the substituent wasn't there, it doesn't matter which carbon you attack, it's the same product. Just the molecule has been turned. All right. Now, we're going to see that again. All right. By the way, is there any proof that this benzyne is the intermediate? Well, there's a variety of proofs. One of them is the benzyne will react in a Diels-Alder reaction. It will react with a diene. Now typically these are made in situ, okay? We can talk about how some alternative ways benzynes can be made, but benzynes will react with dienes, and we can do a 4+2, boom, 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 and that will give a 6-membered ring here. This ring fused to the benzene ring, because right here we will be left with a double bond, and essentially that becomes a standard benzene ring. And if you say, well, if I can get this product, and if I consider this a standard Diels-Alder reaction, then the diene must be reacting with this alkyne, or benzyne. All right, so that's known chemistry, and it sort of lends some proof to the idea that a benzyne is formed here. Okay, but the biggest proof for this mechanism came back in the 1950s when Dr. Roberts at Caltech reported this interesting outcome. And this really helped prove the benzyne mechanism. He took bromobenzene, in which the carbon with the bromine was bonded to was labeled as carbon 13, isotopically labeled. He reacted this molecule with potassium amide, that is the anion of ammonia, in liquid ammonia at -33 degrees. And he got two products. One of the products, the amine, was bonded to the labeled carbon. In the other product, it was somehow next door to the labeled carbon. Well, the mechanism here, and I'll do it on the left since that's where the pi bond is. And by the way, we showed, of course, these are just resonance structures, right? Those pi bonds can be drawn either way. Neither one is correct. I redrew it so I could have the pi bond here, so I could then make the triple bond here. In this case, I'm going to use the H over here because the pi bond would be here. And we can have the NH2 minus nucleophile taking the H. Now some will show the mechanism like this. These electrons move in here and kick off the bromine all in one step. That looks like an E2. And we'll have a triple bond. And that carbon will be labeled. and that was an elimination. By the way, we didn't mention over here, we did an elimination followed by an addition. And that's why the Benzyne mechanism is sometimes considered an elimination addition mechanism. At this point, plus ammonia. Now ammonia acts as the nucleophile, but it can add to either carbon of the benzyne, and that's what it did. All right. If it added to the labeled carbon, we would get that product. I'm not going to do that. How do we get the other product? Well, you've already seen how we add here. Electrons go this way. And that's going to give anion here. Nitrogen with 3 H's. Positive. And we did nucleophilic addition. Now this is dying for a proton transfer. We have a base. We have a nitrogen that needs to lose an H. We need a base to take an H. Intermolecular, H plus transfer. And that will give, I'm not going to show it, but that will give, well, I will show it because be this, and this carbon will be labeled. The nucleophile is next door to the labeled carbon, but that's what that is. All I have done is I've just flipped it over. I'm not going to show mechanism for this one. That would be where we attack the labeled carbon and then we do a proton transfer. But Dr. Roberts' outcome here, he really confirmed that the nucleophile is ending up on the neighboring carbon. This is also an example of using a isotopically labeled atom to sort of distinguish between two different carbons, one that's labeled as C13 and one that's a standard carbon 12 or natural abundance. Okay, in the end, isomers are present or possible. By the way, this was done at cold temperature. That's because the nitrogen anion is such a strong nucleophile. The reaction will work at cold temperature with that nucleophile. With oxygen nucleophiles, like hydroxide or an alkoxide, you typically need very high temperature. So, reaction. You take this, what is this, 4-chlorotoluene, react it with sodium amide in liquid ammonia, which by the way is liquid at minus 33 degrees. That's why that's the precise temperature there. We predict two different products. With the benzyne being that there, and then the ammonia nucleophile adding to either the paracarbon to the methyl or the metacarbon to the methyl. Okay. Here we have a substituent. Do the next two for homework. I didn't leave much room there. You can work on scratch paper. This one gives two major products. Think about the conditions. There's a workup step there. We talked about that. Traditional sodium amide reaction, liquid ammonia. Actually, here you get three different products as major products. See if you can think about how you can get 3. And I'll give you a hint. It's because there's 2 different benzynes that can be formed. See over here, there's only 1 benzyne that's going to be formed. Or here, only 1 benzyne, but in this case, two different benzynes. Please show them both and then see how you get 3 different major products there. Okay, let's end with some stepwise benzyne reactions. We can make a benzyne in situ, and then we can come in with other reactants. We already saw a Diels-Alder reaction. But a way to make it in situ and to not have any nucleophile around is to use n-butyl lithium. All right, carbanion. And these electrons can take the H. Again, we could either show a carbanion and then show the elimination of the leaving group, or we can do it all together. And that would give the benzyne plus butane. Now, butane is not going to act as a nucleophile. And so this is just going to sit there, and we can throw in other reactants. See, in our previous examples, if we use, for example, potassium amide, we create the benzyne plus ammonia, and ammonia is going to act as a nucleophile. And over here, if we use KOH, we make our benzyne plus water, and water will react as the nucleophile. But if you use n-butyl lithium, you produce butane, and it is not a nucleophile. There's no lone pair there. And so we can maybe throw in a diene and do a Diels-Alder reaction. You can show that product. We can throw in a Grignard nucleophile. Think about what that would give. Then that product, we can throw in something like ethyl bromide and then get another product. See if you can rationalize and show these products. Now, one of the last things I'll add is there's actually an interesting way here to make a benzyne from a dihalide reacting with magnesium metal. Now we know this looks like a Grignard, right? And what happens is the magnesium inserts and you get a Grignard at one site. Of course, this Grignard can be considered the anion, right? And then the magnesium 2 plus and a bromide minus. If we show it all ionic, right, we consider Grignards as if they're carbanions. Nothing new there. But what can happen here? That right there looks a lot like that right here. And these electrons will move in here and kick off the leaving group, and that will give the benzyne. And this is actually a fairly common way to make benzynes. It's actually pretty creative and ingenious. And hopefully you see that the chemistry is fairly straightforward. So we didn't use a base to get to this point here. we used an oxidative addition of the magnesium to get to this point. All right, so some stepwise benzyne reactions. I drew all over this, so maybe some scratch paper. See if we can predict product here and then here. Now this product here is going to be an intermediate, really. It's not going to be, you're not going to be able to isolate it. But then if we throw in this, we'll get a fully neutral product that we can isolate. See if you can figure that out. I also show some stepwise benzyne chemistry over here on the warm-up page, and I have an epoxide here. Please also look at that for homework. Okay, that's the benzyne mechanism. It's a very interesting mechanism. I hope you would agree. That mechanism takes place when you do not have a strong electron withdrawing group ortho or pair to your leaving group. All right, let's see what type of questions come up about the NAS and benzyne mechanisms.